Hello everyone, I am MD Rahman and I welcome you to my lecture series on power system state estimation. So what is state estimation? State estimation is the process of removing noise from the measurements. To monitor the power system properly, we collect measurements from different parts of the system. The collected measurements contain noise or error. In state estimation, we remove these noise and we try to achieve the actual values of the states. In power system, the most prominent estimator is the weighted least square estimator, which is also known as WLS estimator. It was invented by Edwin Marie Legendre and Carl Friedrich Gauss in between 1805 and 1809. It can be mathematically proven that it is the most efficient estimator if your system contains Gaussian noise. It was proposed for power system by Fred Schiff in 1970. And since then, it is used as the most popular estimator. There are two main types of weighted least square estimator. One works with the DC or linear power flow equations, another works with the AC or nonlinear power flow equations. So they are called as DC or linear state estimator and AC or nonlinear state estimator. So what are the measurements we collect in power systems? For example, this is IEEE 14 bus system. We collect the real and reactive power flows of the transmission line, real and reactive power injections of a bus, the voltage magnitude of a bus, current flows of the transmission lines, and with the newest PMU technology, we can also measure the phase difference directly. In power systems, we take the voltage magnitudes of all buses and voltage angles of all buses as the state variable. If we know them, we can calculate all other variables easily, like the real and reactive power flows and injections. They can be calculated directly if we know these things. So these are called the state variables. That's all for now. Thank you for watching. Hello everyone, welcome back to Power System State Estimation. In the last class, we were discussing about state variables. The voltage magnitudes of all buses and the voltage angles of all buses are considered as state variables. All these state variables form a vector and we call this x. However, as the voltage angles are relative variables, we need to take one bus as reference. We take theta 1 as 0 and we remove that from the vector. So if there are n buses in the system, then the total number of states becomes 2n minus 1. State estimation is applicable for overdetermined system. What does it mean by overdetermined system? If a system has more equations than the number of variables, then we call it an overdetermined system. In our case, if we have more measurements than the number of states, then we call it an overdetermined system. State estimation is applicable only for overdetermined system. If we have m measurements and the number of states is 2n minus 1, then m must be greater than 2n minus 1. If m becomes equal to 2n minus 1, then the problem reduces to power flow solution or load flow solution. So what are the differences between DC or linear state estimation and AC or non-linear state estimation? In DC state estimation, only the phase differences are estimated. All voltage magnitudes are considered to be 1. Under this case, the reactive power Q becomes 0. And we collect the real power, the voltage magnitudes, and some other measurements. We do not collect the reactive power. In DC state estimation, the power consumed in the transmission line is considered to be 0. If the power flow from bus 1 to bus 2 is P12, and the power flow from bus 2 to bus 1 is P21, then P12 becomes equal to minus of P21. However, in AC state estimation, this is not true. We consider that there will be some loss in the transmission line and they will not be equal. It is also true for the reactive power as well. So these are the formula for real and reactive power of a transmission line. These are the two basic state equations for state estimation. These relate the state variables with the measurement. These are the power flows of the transmission lines. So if the voltage magnitude of bus K is Vk, the voltage magnitude of bus M is Vm, then the power flow, real power flow from bus K to M is given by this equation, and the reactive power flow from bus K to M is given by this equation. If we know these equations, then we can easily calculate the power injections of a bus. These are just the summation of the power flows of the transmission lines which are connected to the bus. That's all for today. In the next class, we will discuss about the Jacobian matrix. Thanks for watching.